Well, good morning, everybody. Thank you for coming here to hear a little bit about, I think, what I would call generational type of events that we're having to deal with here. The original idea for this actually did come from Brad, who called me up, and I said, yes, absolutely, it was an exciting opportunity. Little did I know that, as he said, eventually, I think it was, a week ago, he said, David, it's all yours. So in that context, I'm very happy that we still have an outstanding panel here who, as you'll see in a minute, really span geographically, technically, many aspects of Helene and a little bit of Milton. To start with, and I think I'm ready to advance the slides, which I guess I'm in charge of. So just to put a little bit of context, Hurricane Helene was what I would like to think of as a double hit event. We're used to thinking of hurricanes and as a coastal problem. Other parts of the country, we say that's Florida's problem, maybe a little bit North Carolina on the Outer Banks, and occasionally up all the way up to the Northeast with events like Sandy and so on. Helene represented a variation to this in that it impacted coastal Florida and other states in between, and then ultimately impacted western North Carolina. The characteristics and consequences, however, on the coast and in the mountains were clearly different. Even though they all fell under the umbrella Helene, they were quite different. While this might be considered to be a rare event based on sort of history, looking back in history, it is not clear that it won't become the norm in the future. As we're dealing with climate change and larger scale events, we should perhaps be ready to expect double hits and maybe even triple hits eventually, depending on what happens. So accordingly, I think it's very important that we study and learn from Helene to be better prepared for future double hit events. Now, in order to help us do that today, we have a panel together here, and I'm going to introduce them all at once here at the start, and then as we get into the presentations, they will just automatically cycle up and come up here. But there is a reason and a purpose behind every one of them. Again, both what I'm going to say is geographically and technically. And in fact, as we do the presentations today, we're going to start down at the coast, and we're going to work our way up towards North Carolina. We're also going to see information that was actually being gathered before landfall, during landfall, and post-landfall and post-arrival in North Carolina. So without further ado, our four panelists today are Nina Stark. Nina is an associate professor at the University of Florida and widely regarded as one of the preeminent coastal engineers. She really spreads across the geotech and other nearshore engineering initiatives. Next will come. There must be a bunch of gators out there somewhere. Next is Jonathan Hubler, and Jonathan is from Villanova University. He's an assistant professor, and Jonathan was part of the GEAR team that responded both to Helene, but also then a second phase of the effort that took place following Milton, and so he'll share with you some of the more geotech work that he did. We then do a massive leap over Georgia and go to North Carolina, western North Carolina, and our third speaker is Philip Prince, who is a geologist, and I believe he's a Hokie, if there are supporters out there in the crowd. And Philip, if you think that Nina and John put on a lot of miles walking around coastal areas and doing recon, Philip has put an equal number of miles going up and down mountainsides and debris flows and landslides in North Carolina. And just as a little shout out, obviously I hope you have a chance to interact with all these folks after the panel, but after you get back to your homes as well, look up Philip on YouTube, because he's got a whole series of YouTube videos where he actually takes you along with him walking down debris flows and everything in western North Carolina. So a wonderful trove of information. And then finally, our fourth presenter is Ryan Rassanen, who is an assistant professor at University of North Carolina, Charlotte. And Ryan is kind of going to try and bring a little bit of looking much more towards the future when he tells us about some work that he's been pursuing. You know, we all know very well that there's a massive I-40 project being undertaken, very well funded, or well funded. John, don't tell John Wallach, like I said, very well funded, just adequately funded for John. But Ryan is going to be talking about a different aspect where you could actually say the opposite is true. Very little funding, but I think some very neat solutions there. So without further ado then, I'm just going to spend a couple more minutes with a couple of slides to kind of set the context a little bit more. So one of the things that, as I've been thinking about Helene and Milton, is that we really need to come back and I think and spend more time thinking about resilience, and resilience perhaps in a different, slightly different framework than we've historically done. This is sort of a very classic resilience framework that we typically use. You can see we're moving along, and suddenly we have a disruption. We fall into the valley, and we start to focus immediately on how quickly can we come out of the valley, and we may come to a partial recovery or a full recovery. And while we're talking today about some climate change events, clearly this is also pervasive across many other events. If I think about that, and I think about how we have evolved in our thinking with respect to climate change, I adapted this from originally the original figure came from an author called Perek, who was talking about adoption of technology by society. But to me, I think it also speaks very nicely to the adoption and thinking about climate change and how we respond to it. And you'll see that on the bottom, there's sort of people, processes, technology adoption. There are two y-axes. On the left, I have reward, which at the bottom is going from low to high. And on the right-hand side, I have an axis which is risk, which is going from high to low. And if I go back to probably, there's also sort of four major areas underneath that time span or that process, which are basically unaware, reactive, proactive, and predictive. And if using the graphic on top, maybe with respect to climate change, I'm not saying these are finite numbers, but in around the 2000s, we were probably pretty much unaware. We weren't doing a lot of thinking about what the implications might mean for us. Now in 2025, we're probably somewhat reactive, we're somewhat proactive, and we're somewhat predictive. So I've put a rather large ellipse there because there isn't just a small finite activity. And really where we should be trying to get to is when I've optimistically maybe put a 2050 circle, where we need to really be getting to be predictive, because I think if we can do that, we can dramatically reduce the impacts on society and infrastructure. So as a first step, here's maybe a sort of a slight modification to the traditional resilience curve. And there's two sort of larger changes there. You'll notice now there's no longer a constant value and then a drop down into a valley, but rather I'm showing some form of a dashed line. And what I'm really trying to indicate there is that with climate change, there may be certain degradations occurring, and if we're not carefully monitoring what's happening, we may think we're still at a constant baseline, but in reality, we have much less of an event which will be required to drop us down into the valley. And on the other side of things, we also need to be thinking about beyond just partial and full recovery to things like transformative recovery, and there are activities being done, for example, in the earthquake world that are thinking about that. But perhaps even beyond that with climate change, since it is very much an evolving scenario, we need to be thinking about radical adaptive recovery as well. Now, embedded in then using sort of a curve like this is the concept that the climate change is going to affect what the magnitude of an event that may actually take us down into the valley. And then more importantly, the concept of time to event or time to recovery is also going to change. So moving forward, we need to be thinking about an even richer approach to this. So if I do that, then maybe, and I'm showing a number of different scenarios here, there's the original constant baseline, which had dropped down, but as you can see on the right-hand side, I'm now showing these different recovery states. I'm showing a dashed blue line like I did on the last one, which is showing sort of the degradation before the actual event. But then you'll notice that there are two green lines, one showing a lesser valley, and one showing, in fact, we almost jump across the valley. And I think that those two green lines are really representing what we need to do and where we need to be going. If we start doing things early on, if we're aware of what's happening, we can start to make adaptations, and ideally we avoid that valley altogether, but at least if we can minimize the depth of that valley and the impact, I think that that's going to be critically important. So then, bringing all of this back to sort of resilience. First of all, sometimes people think of resilience more as a concept, but quite frankly, it's quite quantifiable. And I'm using one very simple example here. Here are some histograms of different hurricanes. The blue bars this is based on nighttime lights. You're all familiar with the fact that there's satellites going overhead and they're recording the luminescence from lights. This happens to be black marble nighttime light from NASA. And the blue columns are showing the pre-event variation in nighttime lights. Some of those variations are obviously reflective of whether it's things like clouds or and so on and so forth. But you'll notice then that there are red bars, which are all the bars corresponding to the post-hurricane impacts. And if I just simplify it, you can see here I've actually got some very classical resilience curves showing up here on this particular graphic. So then let's finally move towards Helene and Milton. And in this particular case, we have used power outage curves, and in a minute you'll see that we actually got the power data for every county in Florida, Georgia, South Carolina, North Carolina, Alabama, Kentucky, Tennessee. And we literally generated these resilience curves for I say we, postdoc working with me, Danny Zhang, did all the hard work. We generated these curves for each county. And it's quite interesting. They all tell a different story. For example, this one, which is for Sarasota, which is further south down on the coast in Florida, you can see that while for our initial thought is that Helene was bigger than Milton, in fact, in terms of the resilience here, Helene had a small effect, and then we recovered that in that yellow part of it, and then Milton hit, and obviously that was much more significant for Sarasota County. If we do that for all of these different counties throughout that entire area, you will see that, and I've highlighted some of them here, some of them there's only a single blip. They were unaffected by either Helene or Milton, and vice versa. Some there was a very large impact, and what we did for all of these curves for all the counties, we actually calculated what we call an area under the curve. So if you just jump right across that constant baseline, calculate the area of the curve below that. And when we did that and then plotted them in terms of the counties, we can generate these particular maps. On the left is the map for Helene only. And you can see two things. First of all, obviously a lot of very damaging high area under the curve values going all the way up to North Carolina. And I would notice that there is the line, the trace of the actual hurricane path is shown there in black. And what is quite fascinating is that you've often heard you're better off to be on the west side of a hurricane than the east side. This data shows it exactly, and it's not just a concept, but you can see basically that hurricane path almost defines a line to the east of which all the damage is occurring. The middle plot is for the corresponding for Milton, and so you can see that there was more significant damage, obviously, on the path of it that really cut across the tip of Florida. There are some dark colors up in the mountains in Helene there, but that's actually reflecting the legacy effects of Helene up there. And then the map on the right is the compound one for all of them. So one of the things that I wanted to try and do with this is to sort of show, set the context for how these all are actually in the end tied together, and there's lots of wonderful data sets out there that we can use to understand resilience and what is happening. And with that, I'll hand off to Nina.
Thanks, David. So after this overview, let me take you back to the coast. So Helene was predicted to make landfall on Thursday. For us, Helene really started on Sunday before, because on Sunday we started talking about, is it worth mobilizing? Is this worth collecting important data? On Monday, we made the decision that it would, and we decided to mobilize. And then chaos for us broke loose, and I hope this slide kind of represents that. There were a lot of questions to answer. When and where actually the hurricane will impact? What type of expertise do I need to bring in to collect the right data? How do I get the people there? Which airports will function? How can I make sure people can leave again safe? In particular with this goal to collect data during and before the hurricane, what means you're a very, very tight timeline. A lot of people were involved in that. A lot of organizations, we had to figure out how are we paying for this? How do we get the people here? And so this slide I put in just to give you an impression of that. I felt like a combination of more of a project manager, a travel agent, a fundraiser, and so we are really thankful for the Nearshore Extreme Event Reconnaissance Association, and of course for the Geotechnical Extreme Reconnaissance Association, and NSF and ONR, who were immediately on board and made this really possible, and all these people who were involved. Okay, so Helene made landfall near Perry, and we did have data sets from just a couple of weeks before, a little bit south in the areas of Cedar Key and Horseshoe Beach. And that was a major motivation, because we thought that means we do have relevant data from before the storm, and so we can actually establish a comparison. Also talking to my colleagues from coastal engineering and from storm surge prediction, they said, at that time, it was not really clear, will it be a Cat 2, will it be a Cat 4, will it go to Tallahassee, or will it turn a little bit more right? However, we were pretty sure that this area would see something, and for that reason, and for the reason of planning and mobilizing, we said, okay, let's go there, because we have to make a call where to go. We cannot wait until an hour before, we have to mobilize now. So we made the decision to mobilize on Monday. We started traveling, preparing equipment on Tuesday. We were out in the field on Wednesday. And then the second part, Milton impacted around Siesta Key, and then there were these two major breaches, Midnight Pass and Milton Pass, where the barrier island was opened up, and those became our other major sites. So we are looking at 5 what we call primary sites, where we really wanted to focus, instead of having a lot of information from a lot of different places, we wanted to focus on very in-depth information from 5 primary sites. Okay, so how does it look if you go before hurricane? So evacuation orders are in place, the police is informed. They are actually making sure we're getting through to everywhere. We want to deploy sensors. We installed 21 wave gauges, and we collected LiDAR and aerial imagery in 7 key locations, all that one day before landfall while evacuations were going on. And also keep in mind, we actually had to get on private property, right? To get to these key locations, it was not all public land. So I spent probably on Tuesday and even Wednesday morning hours on the phone talking to community members, and I was blown away. I didn't have one single person who did not pick up the phone and who was not supportive. So that made it possible that we could actually spread these sensors around the whole town or these different places so that we have a really good coverage. And as I mentioned before, we had pre-existing data from June and July that we knew would be helpful later on. So what did these wave gauges, for example, collect? So this is from a location in Cedar Key, and you see what the wave gauge here corrected for NAFD 88. There's a few other corrections that still have to be done. I don't have a curve. What is usually the water level, you see the normal water level in the background on the photo. That was on the day when we installed the gauges. And you see we had about 4 meters of water on top of that. That was really, really high. And if you turn around after the hurricane impacted, houses were gone. There were huge scour holes. There's a complex just a little bit down the road that now looked like an impressionistic picture because of all these different settlements. So the storm surge went in there. It's all sandy material, very erodible. A lot of material was moved around. We saw seawalls slipping in. There was a lot of damage. So we went back, impact on landfall again as a reminder. And then we went back on Sunday to collect the sensor and get initial impressions and make a plan where to go from here. And as you can see, the damages were severe, so we did want to go back and collect this detailed data. So then for the post-reconnaissance, so here Milton got in the way, and we really wanted to collect interdisciplinary data, so we want to get all aspects so that we can get a comprehensive picture of what is going on. We had at times 32 researchers, technical staff members, and students from more than 10 institutions, federal agencies, and industry partners in the field at the same time in different groups collecting this data. We collected really cutting-edge data, used modern technologies. You see a few of the images here. We had drones, we had remote boats, we had other boats in the water. We really tried to hit it with what our profession can offer to get really detailed data here. We focused again on our priority areas, and again, this was in very close collaboration with local authorities and the homeowners, because keep in mind, these places were still sealed up, right? So you needed actually approval to get in, and everyone was so supportive, and I do believe that this data set is maybe one of the largest and most diverse hurricane-related reconnaissance data sets available to date, and is currently published, but also we are still adding to this data. So to give you a little bit of a quick idea of what this data looks like, so important to me was this hurricane, and in particular the storm surge, is coming from the water to the land. So you have to have seamless data from water to land. If you only focus on the land, you will miss half of the story. So in the water, of course, bathymetry, side-scan sonar to image the seabed. What is the hydrodynamics now? We measured pore pressure under the storm surge in multiple locations. We measured sediment strength, where would the seabed softening up, and we collected a lot of samples. So just as an example, I don't know how familiar you guys are with side-scan sonar. It's a way to image the seabed, and that way you can actually see, like in one of the small examples here on the right cut-in, how the bank actually slipped in and practically moved sediment into the channel. We also found quite a bit of debris in the navigation channel, and you can visualize that with this technology. Onshore, and Jonathan will talk a little bit more about that, LiDAR for topography, multispectral imaging. We did jet erosion testing in the field, penetrometer testing, seismic profiling. So again, we have actually very comparable data offshore and onshore to again get that seamless picture of what happened. If you're interested in this data, so after the hurricane, after we were back of the field, actually one of our priorities was to get the data out to the community, to you guys, so that people can use it for studies, for proposals, for looking at what actually happens. So the data is already available on DesignSafe, so go check it out. We will provide data updates every 3 months for probably a year, maybe more time to actually still clean up some stuff, but we wanted to make it available as soon as possible. So some quick concluding remarks. So if you want to do pre, during, post-event data collection, that is really important to create a detailed data set, to create these case studies that show you the comprehensive event-related change and the impacts. Multidisciplinary is really important because it's a multidisciplinary problem, right? So we have to bring in our partners from other disciplines. Again, publication was a priority for us. I think sharing the data, it's just too much data. I mean, I could not write all these papers, you know, even if I would want to. So please go ahead and look at the data. And again, I want to highlight that this would not have been possible without this amazing team, and everyone was so committed, right? I mean, we changed flights like multiple times because Milton got in the way. Preferred airports were changed, all of that. So that made really a big difference. Thank you very much.
All right. Good morning, everyone. Thanks, Nina, for kicking that off. And I hope you got a feel for the massive data collection effort that occurred. I'm going to focus a little bit now on some of the geotechnical impacts and assessment. And I'm really going to look at two locations. So Cedar Key is up in the Big Bend area, and that was where Helene made landfall, near that area. And then Midnight Pass, which is south near Sarasota, and that's where Milton made landfall. And they're two different sites that had two different types of responses. So we're gonna take a look at those. So this is just some more photos of some of the damage in Cedar Key. The storm surge in Cedar Key was 9.3 feet, which was a historical record for the area. And obviously, that storm surge had a lot of impacts and destruction that you see in the infrastructure in the town of Cedar Key. And so a lot of debris everywhere, really from the power of that storm surge. Midnight Pass was a barrier island there, a little south of Sarasota, and you can see that it breached during the storm. And so we were interested in studying this site to really capture all that sediment movement that occurred following the breach. So some of the geotechnical and soil testing that we did included a Panda dynamic cone penetrometer. So the top photo there is the Panda DCP. It's instrumented. It's useful in reconnaissance work like this because it comes all in one Pelican case. You can get your dynamic cone resistance down to about 4 meters or so with the rods in the box, and it's mobile, right? And so this particular site, we had to get there by boat, and so it's nice to have something that can be mobile like that. In some of the data I've collected at other sites, it compares well to the CPT cone tip resistance. We performed ATOM MASW testing to get shear wave velocity profiles at some of the sites. The University of Florida team had the portable freefall planetometer, the Blue Drop, to get some of the shallow stiffness of the soil, like the quasi-static bearing capacity. The jet erosion test that was brought by NC State researchers to get erodibility, again, of those surface soils. And then, of course, soil sampling for characterization back in the lab to get things like grain size. I'm going to just focus a little bit on some of the Panda DCP measurements and show you guys some of that data, just to give you a little picture of what happened with some of the movement and erosion and such. So this is Cedar Key again, and we tested both beaches and mudflats here. So this location was a beach in town. And so this is a sandy soil site. Over here, we went to a mudflat where there was some infrastructure damage and houses that were damaged by the storm surge. The airport site was a transition in this bay from the fine-grained soils to more coarse-grained shelly soils. And then in town, there was a retaining wall that performed poorly, and we captured some data at that site as well. Just to give you an example, we'll look at one site. This was the airport site. Again, with the storm surge, you can see some of the data. The top photo there shows a dumpster that was translated some distance by that surge. The house, unfortunately, suffered severe damage from that storm surge. So we did our suite of testing, and this is what some of that looked like. So we had the MASW system set up there. I should mention that the MASW system and the Panda are both available from the Neary Rapid facility at the University of Washington, so they're available for the community to use. So we had that, we had the Panda, we had the jet erosion test, and if you look up on the dock there, Nina's sitting up at top making sure we're all getting the data and guiding us along our way. And so what does some of this data look like? So this is a plot of your cone resistance from the DCP versus depth. And across this nearshore area, you can see the black line is as you go further inland where you're getting some of those sandy, shelly soils. And the yellow and red lines are as you move into that, fine-grained mud that we had there. And I want to kind of point out here that that spatial distance was not very far. And so you see kind of these sharp transitions in soil stiffness and soil strength. And that's not really captured in current coastal models. Just to switch up a little bit here and go down to Midnight Pass to show you some of those results. So here's the breach. The first test I'm going to show is on the Gulf side, and there's the DCP resistance from that one. Moving across the barrier island, you see some of the changes in stiffness. This one we punched through and got into some of the softer fine-grained soils below. And then going further towards the other side of the island there, you see that you have a significant decrease, right, in the stiffness there. Again, highlighting that in these relatively small spatial distances, you're seeing a lot of change in the strength of the soil. So a couple of conclusions from this. You can rapidly collect post-hazard data. In this example with the DCP, we were able to do a lot of different tests and get these profiles fairly quickly to assess some of the sediment changes and sediment movement. We saw significant changes in soil strength in those upper meters within the short distances across the shoreline. And really, this soil variability is not currently captured in many coastal hazard models, right? And they're relying on things like median grain size as the inputs in these models. And we're excited that we were able to capture this data set. And it's out there for the community to use. And hopefully, we can work to update some of these models. All right, so that's what I wanted to present. So we'll move on to the next one.
Okay. Thank you very much, folks. Interesting for a mountain geologist to see some of the coastal impacts of these events. This will be a change in gears here because everything I'm going to talk about are the impacts of Helene on the North Carolina high country. And within a very short period of time on that Friday morning, landscapes like the one you see here ended up looking something like that. This is one of a tremendous number of very significant debris flow events that occurred when the remnants of Helene passed through the high country. There had been a significant precursor rain event. Everything was saturated, and you put rainfall rates of inches per hour on top of that, and that generates tremendous debris flowing, and that was actually expected for this region. Give you a sense of what you're looking at, that twig there in the middle of the image is actually a 90-foot poplar log. And that gives you some idea of what debris flows like this actually transport in the mountains of western North Carolina. You can see boulders within that deposit as well that are about 20 feet long in their long dimension. And of course, if material like that comes into contact with structures, with people inside, it produces terrible results. Now, the debris flow that I showed you there is going to be the top yellow dot there, the large yellow dot. In lower left, it is Asheville, North Carolina. 3 examples. I'm going to go from top to bottom, but here, of course, we're looking at the very rugged topographic backdrop of the Appalachian Blue Ridge. And the debris flow we're starting with here is very classic in terms of where it moved down the slope. It started at high elevation and a steep colluvial hollow. It followed a small stream channel downslope, and then in this case sort of spread out onto an area that is already mapped as being essentially the deposits of previous debris flow events. It's interesting to look at this with LiDAR imagery draped over it. That allows you to see the details of the landscape that produced this particular debris flow. And of particular significance here is the fact that it sort of overshot the topographic channel at the base of the slope, which caused it to spread out. In this case, it really didn't do much damage, but it's notable that if houses had been positioned differently here, we would have been looking at a very different outcome from this particular debris flow event. Others like it in the area were extremely destructive. The one we're looking at here, if you look at the satellite imagery, this is geo-referenced aerial imagery taken probably a week or so after the storm passed through. This is the middle dot from the map image. Outline that and take a look at the LiDAR setting here. It's a fairly similar one in that the debris flow originated in a steep colluvial hollow, followed a channel downslope, and then spread onto older deposits below. This one's particularly interesting to look at because of where it began. That little outline there is where it kicked off. It began actually as a small translational landslide, colluvial material sliding off of bedrock. It's a pretty small area, about 55 feet wide. That's what it looks like. Appalachian Landslide Consultants founder Jennifer Bauer standing there to give you a sense of scale. You can see the bare bedrock that was revealed by the thin colluvial layer sliding off the top of it. Interesting details here, the yellow line, you can actually see mud lines on the trees here right below that failed area, so it accelerated very quickly, it fluidized very quickly, and in the far distance, you can actually see where the debris flow ultimately ended up on one of those flat deposits. Now, starting off from that 55-foot wide small landslide, ended up producing the effect that you see there. Of course, that wiped out several buildings. Fortunately, they were unoccupied, and that's nothing more than a stroke of luck here. This is what the end results look like. And the physical scale of the deposit produced by that small starting landslide was absolutely immense, about 200 feet wide, about 1,800 feet long, and probably 3 or 4 feet thick. So from a very humble beginning, so much material was entrained on the way down due to the saturated condition of the slopes that what ultimately reached the valley floor was something, of course, totally different from what started off high on the hill. And what you're seeing here is really one of the biggest challenges with understanding debris flow hazard in the Southern Appalachians. That's the questions that was on the title slide. Where exactly are they going to go? What's the run out going to look like? How wide will it be? Things like that. And those, of course, have proven and continue to prove to be very difficult to answer. Probably no location shows this any better than the one you're looking at now. This is in Buncombe County, the bottom dot from the beginning of the presentation. This is the community known as Craigtown. It's in the Fairview area. And if you'll keep your eye on the cluster of houses towards the center of the image and below, if we show the debris flow impact there, there's probably about 6 structures just in this image that are completely gone, and if you were to continue the image further down off the bottom of the screen, you would see that trend continue. This was the deadliest debris flow event from this storm. I believe in the one you're looking at here, there were 8 fatalities, and this was actually sort of a two-pronged event. There was another debris flow to the west that claimed 5 lives. This absolutely enormous in its scale. The hazard area down there was over 300 feet wide, and there were no available hazard mapping products that really gave a suggestion of the potential of a debris flow impact of that scale on this particular part of the map. If you take a look at the mountainside where this particular event happened, rough topography. This is a southeast-facing ridge, so it received upslope rainfall with the remnants of Helene. That's the area that we just looked at in photo. And Appalachian Landslide Consultants uses sort of a susceptibility model to try to indicate where debris flows may begin in the landscape. That's the purple areas. You can see there's quite a lot of them. That's designated by slope steepness, slope shape, concavity, and topographic relief in the immediate area. And if we draft all the debris flows there onto that, it turns out that they began in areas that you would expect them to begin in. A lot of areas there did not fail in this storm. We don't understand why, nor do we fully understand why these particular debris flows were so voluminous and traveled so far. What they look like up on the mountain, that was all, of course, forested and had a few feet more soil on top of it before the event. And if you take a look at something like that, multiply that by about 10 or 12, that's actually what was affecting the communities downslope. And of particular interest on this mountain is the nature of the geology. It's a very micaceous bedrock. It tends to be very platy and slabby. The size of the fragments and the shape of the fragments being transported by the debris flow is a bit different from the other examples. And it's possible that variables like that are actually contributing to the mobility of debris flows in certain parts of western North Carolina like these. So there's quite a bit to learn in the area. And with the Helene event, there's an extensive record of what happened, probably the best record of what has happened in an event like this, if it even has counterparts in recent history, which it probably doesn't. Hopefully we'll be able to take those materials and continue to learn from them and have a better idea of what's coming should we see something like this down the road. Okay, there we go.
Hello, everybody. So if you haven't seen his YouTube videos, he goes on a great field trip of taking you through the debris flow, and they're really awesome, and so you should check them out. So today I'm going to be talking about some of the damage to infrastructure, just at an overview, and then transition into the local level. So you've probably all seen images looking something like this. A lot of infrastructure was damaged from Helene. This ranged from large interstates like Interstate 40 connecting western North Carolina to Tennessee, where the floodwaters eroded away a lot of the road embankment. Also, it damaged numerous numbers of bridges. This bridge on the bottom left here is the bridge to Bat Cave, North Carolina, where the river scoured away the supports and the bridge failed. And just to give you an idea of the forces involved here, you can see there's a freight container right there, and that freight container is absolutely mangled. But it also impacted a lot of roads throughout the entire region, connecting the various communities in western North Carolina. And since Helene, larger infrastructure projects have progressed. So on the left here, this is what it looked like the day after Tropical Storm Helene arrived at Interstate 40. And this is what it looked like last week after a soil nail wall was put in place to stabilize the slope. And actually just this past Saturday, I-40 just reopened one lane in each direction. But however, design solutions for smaller resource-limited crossings have lagged behind a little bit. And so the latest counts, there's been damage to about 8,000 different private bridges, roads, and culverts. So a lot of people still are not able to get to their homes, and so their driveway may look like the picture on the left, or what was a culvert may now be a 15 to 20 foot gap that now needs a temporary bridge, or what was a small stream is now a bigger stream. And the problem is a lot of these are at the majority of these are at the homeowner's expense to repair. And so as an immediate solution, makeshift bridges have been built out of whatever materials were available to get supplies to these homes and communities. A couple examples here, and this is continued throughout since Helene happened. More recently, not quite at the local level, NCDOT has contracted with a company to develop 40 temporary bridges out of flat rail cars. So you may have seen them on railroad tracks. They're turned into a temporary bridge. You weld on a guardrail and you have your bridge there. But there's still several thousand of these temporary bridges and culverts that need to be repaired. And so UNC Charlotte is trying to make a small impact by offering an interdisciplinary tech elective called Lansing Bridge Design. And this is where junior and senior standing students are going to develop low-cost, rapid deployment bridges or designs for bridges that prioritize safety and resilience. And so students are going to get this great opportunity to use emerging tools. They're going to have someone go out in the field and show them how to use drone-based land surveying, use geospatial tools, WebGIS, use building information modeling software like Revit, and in addition to applying their core civil engineering principles that they learned in the classroom to an actual real-life design scenario that has a lot of impact to it. And so we're partnering with Lansing Bridge to Recovery, who is a nonprofit organization that consists of about 10 different volunteers that are going out and constructing these bridges. And so far, they've designed, or they've constructed about 30 temporary bridges, but they have over 220 currently on their list, and there's thousands left out there. And so we've already started meeting with them, and our students have started doing some preliminary analyses, and this course actually started this past January. And so just to give you a general overview of what the students are going to be doing, they're collecting this drone-based land surveying data. From that, they can compare it to existing high-resolution digital elevation models. They can figure out, well, how much did the stream widen during the events? How much fill volume do they need? In addition to, we want to make these temporary bridges resilient. And so we don't want them to fail in a couple of years. And so we want to design them for a 25-year flood, and also to be able to support things like emergency vehicles, fire trucks, and ambulances, and all that sort of stuff. In addition to this, in tandem, we're also partnering with another university in North Carolina, UNC Pembroke, who's going to be looking at this and taking some of our preliminary data as a whole and figuring out how we can optimize the process. And so initially, our goal is to design one bridge per student each semester that we can give to Lansing, but we hope to increase that because there's so many. And so, like I said, one bridge per student per semester. And we have currently 13 students right now. But I think the really great thing is students are getting to learn how to use these emerging tools and apply their civil engineering background to a real life scenario that has an important impact. And so they're getting this really great experiential learning opportunity that prepares them for the workforce. And most importantly, home access is being restored to some of the residents in Western North Carolina. And so I just want to thank NSF and Gear and David for having this opportunity to come up here.
So thank you very much to our presenters. They all stayed close to time, and that the good news is that's given us a little bit of time at the end here to have some Q&A, which I think is always important. I myself find it, this, as I said at the beginning, this is a fascinating event. I think it's a generational, and hopefully with the panelists here, we've given you sort of a sense of various aspects across the whole thing. You know, one of the thoughts that comes to mind, and I've not been endorsed or asked to do this, but it seems to me that this project that Ryan is talking about is a beautiful seed for perhaps many other student organizations to engage with, and could even get wrapped up into some form of a future competition at a future Geo-Congress or whatever. So I love ideas like that have merit in themselves, but can also serve then as a seed for others to engage as well. So with that, are there any questions out there? Yes.
As most of you know, I'm very happy to ask a question. I'm Cassie Rutherford, Iowa State. I was super excited to hear this talk. And I've been thinking a lot, how can we leverage the things that we are doing so that the general public sees the value of what we are doing to help them? So all of the projects y'all discussed about, I think would be amazing for local newspapers to be covering, talking about how federal funding explicitly is helping locals. So how have y'all done that? Are there ways that we can leverage all of this into the current climate and talk to people about why NSF funding, federal funding, and our, federal employees are so important to their day-to-day life?
So I suspect several people may be able to contribute a part of the answer to that. But let me start off by saying, first of all, as you heard from throughout and from the various speakers, NSF was a huge part of much of what you saw and learned here. They supported that, teams going to the field through GEAR, through NEAR, through other direct contracts and so on. One of the great things about that is, apart from the fact that it enables it, they also are very insistent on, for example, data being uploaded into DesignSafe. And Nina mentioned that the data had already been published, and that is within DesignSafe. That's at the University of Texas. That's the activity that Ellen Rathje leads. And the purpose of it being there is that, in fact, that is now your data. It's not just Nina's data, but any ideas that you have and you think you need data, you can go there, use that data to help build on it. So that's one part of it. The other side of it, of course, was and John mentioned this too, but an important contributor in all this activity has been the other part of the NEAR system, which is the RAPID. And they provided equipment and have also been involved with the processing of some of the data and so on. And so there, while the events have happened, there are still opportunities to go and gather additional data if that is desired. I know, for example, personally, I'm planning to deploy a small group up to Western North Carolina to gather some additional data on areas that have not already been quantified with LiDAR and multi-spec imagery. So it's an ongoing opportunity as well. So others here have some thoughts?
Yeah, so we have parallel actually continued to work with the counties and with our communities. So for example, next month we will have a presentation in Cedar Key, and actually before we release the data to us as a research and practitioner community, we actually made sure that the homeowners and the community members who have been so supportive, that they got information practically in real time. So I kept calling them and saying, hey, this is the water level we measured at your house. And so I think that was really, really important also to develop this trust that they saw. We did not just come in, run in there, collect our data and go away and then they never hear from us again, but that we are actually really engaging with the communities. There's a number of NGOs involved who work locally on different problems who we shared data with, and we are actually continuing the discussion with. So another thing that we had discussed was possibly reaching out to some more like popular science outlets if they would be interested in picking up the story. And so we're actually hoping that working with some media people, we would get an article or maybe a little TV contribution actually into one of these outlets to distribute the information, what we are doing, even wider.
Also, quickly, in Western North Carolina, the media coverage was extensive and continues to be, and there's been a lot of valuable communication. There's been a lot of interest from media figures in telling the story correctly and actually using terminology and descriptions that accurately portray what has happened. I'm coming from working with a private company, but we're heavily engaged with both private landowners and emergency managers. And it seems that it's an unfortunate reason to see an increased engagement and interest, but that's absolutely there. And I think this time around, just because this event was so well documented, in our part of the world, things like landsliding, debris flowing, large-scale flooding, just due to land use patterns, forests, the reminders of that go away quickly. They will last longer here, and hopefully they will remain part of the conversation, and stakeholders at all levels will remain interested. There's also a lot more interest, I know for sure, in publicly available products about things like slope hazard. I would say that we have continued work to do in making those more user-friendly, but the ball is rolling after this event for sure.
One other quick thing I'll mention is that I think obviously there's a little opacity right now with respect to certain federal funding and so on and so forth. But something to keep in mind is that there are many foundations out there that are actually looking for opportunities to fund activities. And so spend a little bit of time looking to see if there's a particular foundation that actually your interests and desires might align with, and they could well be a source to help fund some additional work as well. Yes.
I have a quick question for Ryan. How do you handle the liability for those projects when you're getting student work to do that?
Yeah, that's a really good question. So we want them to be as resilient as we can, and temporary bridges are being built out of whatever right now, and so they're going to be doing the analysis, and there's civil engineers at Lansing Bridge to Recovery as well that have been practicing for 10 years, and so they'll see the designs, and the students are going to present to them and give it to them as well. And so this is all just coming together. Lansing came to us just in December, and we've already put the course together. And so this is something that is in the process of happening as we go. And so that's something that I need to think about a little bit more. But the goal is to prioritize safety and for them to be resilient designs, and so they don't just fail within a few years.
Okay, we probably have time for maybe one more question if it's out there.
Hi, I'm Siddharth. I work at Embry-Riddle Aeronautical University in Daytona Beach. We work a lot with the local community, and we do some reconnaissance on our own capabilities right after storm. I was wondering how to get engaged with the broader community. What's the channel to get engaged to the broader community? Because Milton affected us. It was a second-hand effect, but it was mostly a storm event. A flooding event. Ian was a huge flooding event for us. It was never a storm event. So I guess there is some knowledge lacking on that aspect, on how it's not only just a storm surge or a wind impact. It's more than that. It's more like a flooding event. So how to get involved with the broader community on that regard?
Yeah, I think there's multiple stages. So of course, contact David, get involved in gear, right? I mean, to get involved in future opportunities on the work that we have done so far. So go on Design Safe, check out the data products, look what you're most interested in, and you will find that we have actually added little README documents, and they actually describe also who is the person of this big team who has actually worked on this, and then reach out to these people. And we are really excited about seeing people interested in this, collaborating with you guys, or even just like pointing you in the direction of the data, answering your questions, and then have you go with it and use that data. So there's different ways, and we would be excited to have you involved. All right.
Well, I don't see Brad. I don't feel a hook around my neck, but I think we probably should stick with his. Oh, here he is. So thank you very much. A hand again to all the panelists. I think they did a great job. So.